So the mean value theorem for derivatives is pretty straightforward. It simply says that if you have a function that's continuous for every point on a closed interval from a to b, and it's also differentiable at every point on the interior of that interval, so the open interval from a to b, then there has to be at least one point somewhere between a and b where the instantaneous rate of change, or where the derivative, is equal to the average rate of change, or the slope between the two endpoints. That's all it says. So if the function is continuous and it's differentiable on an interval, there's a place somewhere on that interval where the derivative is equal to the average rate of change. So where f prime of c is equal to the slope between a and b, f of b minus f of a over b minus a. Any questions on that?
What would you use this for?
So the main use of it is figuring out a location where a function might have a turning point where a derivative equals 0. Hold on one second. Sorry, did I answer your question or not? I can't remember. I'm having an issue with one of my children this morning.
You answered it partway.
Okay, yeah. So the main reason that we use this is to figure out when a function has on what intervals a function has a turning point. So on what intervals a function has a derivative that's equal to 0. At least that's the main reason we'll use it for. It's also very useful in a lot of other higher math classes like differential equations. When we talk about, it can be used to prove that a differential equation has a solution on a certain interval, which is sort of similar to what I just said, but it's not exactly the same, and it doesn't make any sense to you probably now at this point anyway. There's also some like real world applications of it. Like cops will set up speed traps and stuff like this, where they'll have they'll clock what time you go through. Like let's say it's like you've got those the toll roads and stuff where they like know what time you enter and what time you exit it, and so using this they can say, well, if you entered and exited it this 5-mile stretch, and it only, let's say it only took you 3 minutes to make it through that 5-mile stretch, the mean value theorem will tell you that at some point in there you were breaking the speed limit, and then they'll just write you a ticket for it and just send it to your mail, that kind of stuff. So fun things like that. But that's kind of a basic application of it. The more cool stuff comes with higher math classes. There are 3 or 4 classes beyond this one. So it's not a great answer yet. We're going to use it mostly to find when functions have turning points and when their derivative could equal 0. Does that sort of answer your question? Yeah. All right, cool. So I want to make a point to note that the function has to be continuous on that interval, and it has to be differentiable on that interval in order for this to apply. So please be very careful with that. Make sure you check the hypotheses of the mean value theorem. So if we had a function like absolute value of x on the interval from -1 to 1, something like that, we should know that this does not satisfy the hypotheses of the mean value theorem. Because why?
Because it's not on 0.
Because it's not differentiable at 0, exactly. And then what about the greatest integer function? This is one you might not think about, but this is what it looks like. You've seen it before probably, but you may not be super familiar with it. That one's not continuous on the interval from -1 to 1, and therefore the mean value theorem wouldn't apply for that either. Does that make sense?
Makes sense.
All right, cool. So what we're going to do then is we are going to take a look at a simple function, the function f of x equals x squared, and we're going to see if it satisfies the hypotheses of the mean value theorem and find all the solutions to f prime of c equals f of b minus f of a over b minus a. Good? Understand what we're trying to do?
Yeah.
All right. So first off, is f of x continuous? On the interval from 0 to 2?
Yes.
Yep, and why? Because it is a polynomial. And what about the derivative, f prime, which equals 2x, right? Does that exist on the open interval?
Yes.
Yep, why? Because it is a polynomial. Same reasoning, right? So the hypotheses are met, which tells us that there must be a place where the derivative somewhere on the interval 0 to 2 is equal to the average rate of change on the interval 0 to 2. So we'll say f prime of c has to equal f of 2 minus f of 0 over 2 minus 0. And so what we're going to do is, first off, f prime of c should be 2x, sorry, 2c, right? Because f prime of x is 2x. And then f of 2 should be what?
4.
4. And f of 0 should be 0. So 4 minus 0 over 2 minus 0 ought to give us 2c equals 2, or c equals 1. So the place on the interval from 0 to 2 where the instantaneous rate of change is equal to the average rate of change is at c equals 1 or x equals 1. And real quickly, let's, I'm going to throw this into Desmos. Just, I mean, I know we know what the parabola itself looks like. So there's our parabola. If we were talking about the line that goes through 0, 0 and goes through 2, 4, what's the equation of that line?
Y equals 2x.
Correct. So there's that secant line. And then if I were looking at the equation of the line that had a slope of 2, but went through the point 1, 1, that'd be y minus 1 equals 2 times x minus 1. And we can see clearly that those are parallel. It's tangent to the point 1, 1, right? It's tangent to the parabola at the point 1, 1, and those two lines are parallel. And so we were guaranteed that there must be a place where that was true, and we were able to find the location of that. Good or no?
Makes sense.
All right. So I'd like you guys to take about 2 minutes here and see if you can figure out why both of these functions fail to satisfy the hypotheses of the mean value theorem. All right, ready, go. So for the first one, what's the derivative here? F prime is 1 over 2 root x squared times the derivative of root x, times the derivative of x squared, which is 2x. And clearly 0 can't be plugged into that. And so f prime of 0 does not exist, and therefore the derivative doesn't exist on that interval from -1 to 2. Everybody agree with that? So that one fails to satisfy the part about the derivative. And then this one, if we were to look at the limit as x approached 1 from the left, well, that's 4. And the limit as x approaches 1 from the right of f of x, well, that's 2. And since the limits from the left and the right are not equal, then the function is not continuous at x equals 1, and it doesn't satisfy that piece of it. Everybody good with that or no?
Sounds good.
All right. So I would like you then to try to do this one on your own also. See if you can use the mean value theorem, show that the hypotheses of the mean value theorem are true, and then see if you can find that place where the tangent line is parallel to the secant line. That'll give you about, I don't know, 3 or 4 minutes maybe on this one. Probably won't take that long, 2 or 3 minutes. All right, let's see if you can do it. Ready, go. All right, so first off, is this continuous on the interval from -1 to 1? The answer should be yes, because what is it? It's the square root of a polynomial. And if we square root a polynomial, then it's going to still be continuous as long as it exists on the entire domain. So it's the root of a polynomial that exists on the entire domain. So that's fine. What about the derivative? What's f prime? 1 over 2 root 1 minus x squared times the derivative of 1 minus x squared, which is -2x. And so this should be defined for all of the values between -1 and 1. This exists on -1 to 1. The only places where it doesn't exist are at -1 and at +1. But other than that, it exists for all the values on the open interval. So it satisfies the hypotheses of the mean value theorem. Then we just need to figure out what f of b minus f of a is. Well, that's 0 minus 0, isn't it? Over 1 minus -1. So we're just looking at when does f prime of c, or negative c over root 1 minus c squared, if I cancel the 2's out, equals 0. And the answer to that should be, well, whenever the numerator equals 0, which would be when c is 0. 1 second. All right, so if we got c equals 0, what is the slope going to be there? The slope at c equals 0 should be what? Should be this value. It should be also 0. So if it's a horizontal line at x equals 0, or at c equals 0, that horizontal line should have a y value of 1. So it should be y equals 1. And you should, I hope, all know what the graph of root 1 minus x squared looks like. What does that look like?
A semicircle?
Yeah, it's a semicircle, exactly. It's a semicircle centered at the origin with a radius of 1. And so there's your semicircle. And if you put in y equals 1, there it is, tangent to the function there. And clearly that's parallel to the one that goes through those 2 endpoints, which would just be y equals 0. Everybody good with that? Any issues there? All right, so the last thing that we're going to talk about then is called Rolle's theorem. And Rolle's theorem is just a corollary to the mean value theorem. Rolle's theorem says, well, if the function's continuous on a to b and it's differentiable on a to b, and f of a equals f of b, then there has to be a place where the derivative equals 0 somewhere on that interval. And if there's a place where the derivative equals 0, that tells us there's one critical value on that interval, or at least one critical value. So if we look back at the last one, right, f of a was 0 and f of b was 0, f of a equaled f of b. So really this one is the corollary. This is Rolle's theorem. saying that there must be a place where the derivative is equal to 0 on that interval. There must be a critical value or a potential local max or min on that interval. Does that make sense? It's basically the same thing, except a special case of it. Good or no? Hopefully that's all right. All right, so why don't you guys take a second and see if you can show if this satisfies the hypotheses of Rolle's theorem, and then find the value on the interval 1 to 4 that makes it work out. Ready, go. All right. So we know that both f and f prime are both continuous and exist on that interval 1 to 4, right? Because they're both polynomials. And so all we have to do is figure out what f of 1 is and what f of 4 is and see if they equal each other. So what's f of 1? Should be 4 minus 20 plus 29, which is 13. And f of 4 ought to be 64 minus 80 plus 29, which is also 13. So since f of a equals f of b, that means that there's a place where the derivative, or f prime of c, has to equal 0 on the interval from 1 to 4. And so f prime of c is 8c minus 20. So we know that must equal 0 on that interval, and that would occur at c equals 5 halves. It would appear 20 over 8, right? It's 5 halves. And that's it. Any questions on that? Hopefully that's what you did and what you got. Any questions on the mean value theorem or Rolle's theorem? Rolle's theorem just being a special case of the mean value theorem.